All right, this is gonna be the part two. You know, I'm kind of heated right now because I can't believe that whole discussion about negative and subtracting kind of derailed my last video. The big takeaway at the end was that, you know, as far as the axioms of real numbers, there is no such thing as subtracting. There has always been just adding negative numbers according to the axioms of real numbers, and similarly, uh, there was never such a thing as dividing by a number. It was more like only multiplying by the multiplicative inverse of said number. You know, which again, if you live by that, you'll see that you will be better at math, because again, the subtracting sign, which I'm claiming to be different than the minus sign, right? The subtracting sign is something we should just throw out to the garbage. Same thing with the division sign, and just write fractions instead. All right, so yeah, there's a more to this topic that I really want to talk about, because again, these are the videos that should put everyone in the same page, right? And the last video showed that if two quantities are equal, you can you can add the same thing to both sides, positive or negative, and you still get the same thing, right? And same thing, if your two quantities are equal, then you can multiply the same thing to both sides, and they'll still be equal, right? All right. So what's another rule? What's another rule of algebra that people tell you, but you never really knew why it was true, right? Well, let's touch on negatives, right? Actually, before negatives, let's talk about this statement. A plus B times C plus D equals. So what do they teach in high school? They do a whole thing like that, right? They do something like that, right? So they're saying A plus B times C plus D equals A times C plus A times D plus B times C plus B times D. So why would this be true? So the big reason why this is going to be true is going to be the distributor law. And again, if I were to draw a picture, right? Well, now we're saying that we have this kind of rectangle. One length is side length A, but then the rest of the length is length B. And then on the other side, we have a length C, and then a length D. Let's say right here. So this is like the cutoff points for each ones, right? So then if you found the area of this rectangle, now we cut this cake into 4 pieces. This little rectangle has area AC. This little rectangle will have area AD. This rectangle will have area BC. And this rectangle will have BD. Right? But again, we're given axioms of real numbers so that we can prove these statements without the need of physical evidence, if you say. So what will be the proof? So the proof is kind of still the same, though, that I will be using the distributor law. So for example, the proof is that so we have A plus B times C plus D, right? Well, think of just A plus B as if it was one number, right? If you add two real numbers, you get a real number. Imagine we call it X right now, right? Let X equal to A plus B. So then now we have that A plus B times C plus D just equals, right, equals X times C plus D, right? And then now maybe you see what I mean about using the distributor law, because if I have X times C plus D, then one of the last axioms said that, yeah, X times C plus D equals X times C plus X times D. Okay, well, I'm going to put it equals all the way in the front. So Go back. Well, so we have a plus b equals c plus d equals x times c plus d equals x times c plus x times d. And let's substitute the x back now. So now let's bring it back. So x equals a plus b, right? So now it equals a plus b times c plus a plus b times d. Okay. Now, again, the distributor law usually said that this standalone number should be in the front. Well, we can switch this, right? A plus b times c equals c times a plus b, because again, if you multiply two numbers, you can, a times b equals b times a, and we can do the same thing here. D equals a plus b. So ultimately, right, if this equals to that, I mean, I'll just do it. C a plus b, and then plus a d a plus b. And then what do we do now? Well, again, distributor law, right? Or the axiom of the distributor law. So now we have c times a plus c times b, and then now plus d times a plus d times b. And I mean, if you notice, we do have what we wanted, right? It's just that they're backwards, like obviously a times c times a is equal to a times c. And then what else? We wanted to have an a times d, right? Oh, it's over here. A times d. We wanted to have a b times c. Yeah, this is b times c. And we wanted a b times d. Well, yeah, this one, b times d. So I'm saying that, yeah, as soon as we get to this point, really, we finish proving it, right? So this is a proof that this multiplying works this way when you have a plus b parentheses c plus d, right? When you have something plus something parentheses something plus something, right? So this is why this statement is true. So it's not an axiom, but it's something that you can prove. And it really is just, again, the distributor law used twice, really. Okay, but now let's really talk about negative numbers, right? So, for example, what's one statement that again, so for example, negative b, meaning just the negative of some random number b, equals negative 1 times b. How can we prove that statement? So here's the thing, right? And we might not know anything about negative 1 times b, but the one thing that we do know about negative b is that it's the additive inverse of b, meaning that we know that b plus a negative b equals 0, right? Well, to be more precise, the axiom said that the additive inverse is unique. So if I'm going to prove that this equals that, because of that uniqueness thing, I feel like if I just prove that negative 1 times b is the additive inverse of b, then that's it. That's all we need. So again, the idea is, I know that b plus a negative b equals 0. But that negative b is the only unique number so that this happens. So that's what I'm saying is this. If b plus some mystery number equals 0, then it has to be the case that that mystery number has to be negative b. So what I'm going to do is I'm going to show that if I add this number to b, I get 0. So the proof is that consider b plus a negative 1 times b. Consider this quantity, right? Well, b plus a negative 1 times b. Okay, what's so special about this? Well, b is 1 times b, isn't it? So this equals 1 times b plus a negative 1 times b. Okay, where am I going from here? It's actually, so the distributor law, when we say that, let me just use different letters, just this one case, right? So the distributor law says that a number times adding two other numbers, the addition of two other numbers, equals this, right? Well, the thing about an equal sign is actually that it goes both ways. So the distributor law, in a way, is also the factoring law, meaning if you start on the right hand side, u times v plus u times w, if you start on the right hand side, then you are allowed to go to the left hand side and say factor it out, basically. So that's what I'm saying. The distributor law is really also the factoring law. The reason why factoring comes from the distributor law. So what I'm saying is that I have a b here and I have a b there, so I'm going to factor it. So this plus that equals parentheses. If I factor out the b, I get a 1 plus a negative 1. Okay, but then 1 plus negative 1 has to be 0 because negative 1 is the additive inverse of 1. So then this is 0 times b, which is, and then one of the axioms says anything times 0 is 0. So then I did it, right? I showed that b plus this number equals 0. So if b plus this number equals 0, and again, additive inverses are unique, thus negative b is equal to negative 1 times b. That's what we wanted. Again, we're saying that we're using the fact that it's unique to prove that. What's another thing that people tell you and maybe they don't give you a good enough explanation? Well, let's think about this one, right? A negative number times a negative number is supposed to be a positive number, right? Have you ever heard of a good explanation for that? Well, I think that the explanation for it actually boils down to this one thing, statement, right? I think that if we can prove that negative 1 times negative 1 equals a positive 1, then I think that would prove it. I mean, I'll let you think about that one, right? But I'm saying that if we can prove that negative 1 times negative 1 equals positive 1, right? Well, what it would just prove, any negative number, or you can think of it this way, negative b, is really just negative 1 times b, right? So for example, I'm saying that if you have, for example, why should negative 3 times negative 5 be equal to a positive 15, right? Well, maybe because negative 3 times negative 5 equals, like I said, I just proved that negative b equals negative 1 times b. So negative 3 really equals negative 1 times 3, right? And negative 5 equals negative 1 times a 5. So if negative 3 times negative 5 equals negative 1 times 3 times negative 1 times 5, let me put the negative 1's together, and then let's put the 3 and the 5. Well, I know that 3 times 5 is 15, so negative 1 times negative 1 times 15, right? So if negative 1 times negative 1 times 15 is going to be equal to a positive 15, it better be the case that negative 1 times 1 equals a positive 1. That's what I mean by, maybe the explanation to why a negative times a negative is a positive really all relies on the fact that negative 1 times negative 1 is a positive 1. So let's prove that, don't you think? Let's actually prove that negative 1 times negative 1 is a positive 1. Well, I'm gonna prove this. This one I'm gonna actually prove in two different ways. Let's see. So proof one. Let's see if you like this, right? Would you say that 1 equals 1 times 1? I would say so, right? I mean, no matter how you look at it. Okay. Would you agree that 2 minus 1 is 1? Is 2 minus 1 1? Yeah, right? So I'm going to substitute this 1 by 2 minus 1. And I'm going to substitute this one by a 2 minus 1. So as you can see, I'm going to do some type of trickery. Let me expand this moreover, right? So I'm not, like I said, I don't really like minus signs. So I'm just going to say 2 minus 1 is 2 plus a negative 1, right? And over here, same thing. 2 plus a negative 1. Okay. Well, now I know how to use multiply this scenario, right? According to what I just proved at the very top, it should be this times that, 2 times 2 plus 2 times a negative 1 plus a negative 1 times 2, and then plus a negative 1 times a negative 1, right? Okay, let's do this calculation. 2 times 2 is 4. 2 times negative 1, we just realized is a negative 2, right? Again, by the other previous statement. Negative 1 times 2, again a negative 2. And then negative 1 times negative 1 right now is a mystery, right? It's a mystery. Okay, well, okay. A 4 plus a negative 2 is 2. And then again, a 2 plus negative 2 is now 0, right? So 0 plus negative 1, negative. And again, I might not know what negative 1 times negative 1 is. I do have an axiom that says because negative 1 is a real number, and because negative 1 is a real number, that when I multiply them, I get a real number. And then not only that, but a real number plus 0 is itself, just itself, right? But see where I ended up? I start with the fact that 1 equals 1 times 1, which equals that, equals that, equals that, equals that, equals that, equals that. And now I ended up here. So 1 has to be equal to negative 1 times 1. How do you feel about that proof? So maybe not that satisfied. I mean, I don't know. I like it. But the other way to prove this that might be more mathematical, more making arguments, is that, okay, we know that negative b is negative 1 times b. So negative 1 times negative 1 is really nothing else than negative 1. You see what I'm doing? Again, remember, equal signs go both ways, right? So negative 1 times b is just a negative b, right? So negative 1 times negative 1 is just a negative of negative 1. So I think, so this part is true just by proving that statement. Okay, so negative 1 times negative 1 is, so let me put it this way. Negative 1 times negative 1 is the additive inverse of negative 1. Negative 1 times negative 1 is the additive inverse of negative 1. Well, what's an additive inverse? An additive inverse is the number that you add to negative 1 so that you get 0, right? So let's say that. So negative 1 times negative 1 is the additive inverse of -1. Well, what's the additive inverse of -1? The additive inverse of -1 is the number such that when you add it to -1, you get 0. So what number do you add to -1 to get 0? 1. So 1 itself is the additive inverse of -1. Since 1 is the additive inverse of -1, then yeah, you have to say that 1 is negative of -1. And again, by the thing that we just established previously, negative b equals -1 times b, so negative of -1 is just -1 times -1. So again, the second proof is kind of more mathematical, but I like the first one. Okay, one more thing. I just noticed that I missed something. I think I said that right here, right? 0 times b is equal to 0. I guess I never actually proved that, and it's actually not one of the axioms, right? Well, if it's not one of the axioms, it's something we can prove. So let's prove zero times a equals 0 no matter what real number, right? Now, so in order to make everything after here valid, let's just say that I should have included the statement before this one, right? That being said, if I'm gonna prove this statement, I'm not gonna use any of the things I've proven so far, which is really just two things, right? So I'm gonna prove the statement without using these two things as fact, and that will make it so that we don't have some type of circular logic. Okay, so the statement is 0 times a equals 0 for any real number, right? So again, when you have an equal sign, it actually goes both ways. So usually I start with the left hand side, try to work my way to the right hand side. It's completely fine if you can try to start from the right hand side and then to the left hand side. But okay, let's just say proof. So 0 times a, right? Okay, I'm multiplying, so what if you just use this parentheses? 0 parentheses a, right? But why would I want to do that? Well, 0 is, it's nothing, right? So is 0 equals 0 plus 0, right? 0 equals 0 plus 0. You're cool with that? So then this 0 I can substitute it by 0 plus 0. So what I have, 0 times a equals 0 plus 0 times a. Well, why did I want to do that? Because now I can distribute, right? 0 times a plus a 0 times a. Okay, so far I have that 0 times a equals 0 times a plus 0 times a. And then, okay, just to really nail down this point, right? 0 times a. 0 is a real number because the axiom says so. And I'm saying that this statement is true for a, which is a real number. So 0 times a is a real number. We don't know what it is right now, wink wink, but we should know that 0 times a is a real number. So then 0 times a is the same thing as 0 times a plus 0, right? Because 0 plus any real number is still the same. But what I'm trying to say is that on the left hand side we have 0 times a plus 0, and then we see that this is all equal to 0 times a plus 0 times a. Again, I want to focus right here. Well, because again, the fact that I'm saying that 0 times a is a real number means that 0 times a has a multiplicative inverse, right? So so we're saying because 0 times a is a real number, then there should be a negative 0 times a also in the real numbers by one of the axioms, right? I don't know what it is, but I just know it exists because that's what we said. Any real number has an additive inverse. Well, then add it to both sides. Then negative 0 times a plus 0 times a plus 0 equals negative 0 times a plus 0 times a plus 0 times a. But why did I do that? Because again, that's the whole point of negative additive inverses, right? This all becomes 0. So now we have 0 plus 0 equals, and then now this becomes 0. 0 plus 0a. 0 plus 0 is 0. 0 plus 0a is 0a. And now and then that's it. We proved it. We proved that 0 equals 0 times a. Again, right? I don't think I used the fact that a negative number is just negative 1 times itself, nor did I use that negative 1 times negative 1 is 1. So again, if we just put, if I hadn't forgotten that this statement goes in front, then yeah, this statement now makes this statement valid, and this statement now makes this statement valid. See? No circular logic. Well, yeah, sorry, I forgot that, right? But yeah, now you know 0 times any number equals 0 is actually not an axiom. It's actually something you can prove, and this is how we proved it. Alright.